right?
Yeah, I have my sister-in-law.
Okay, that helps. Yeah, it's surely an incentive. Ken said he is not well, so he was asking me if he can join from Zoom, and I said should be fine. Might show up also. Yeah. But you didn't go to Florida, right? During winter break?
Winter break. I'm planning to go there. I won't go there because
You're going to go where?
I'm planning to go in the lab.
Oh, in the lab.
Yeah.
Okay.
I haven't gone there since 2 weeks.
Okay, because
Yes.
too many things coming up.
Yeah.
Yeah, I can just. Yeah, you can catch up. During. Like talking about traveling, I've never been to Grand Canyon. That's a big, very good spot. One of the most.
You been to Smoky Mountains?
No, I never. I've crossed that. Been to this one. I've driven through it, but I never.
I had the Smoky Mountains also.
Yeah, but when you traveled to Atlanta, you did that.
No, I never been to Smoky Mountains.
Okay.
I have been through Tennessee. Well, Atlanta, I went to Tennessee. But I heard that Smoky Mountain is a good place.
Yes, that's correct. Yeah.
Norway is also beautiful, I think.
Oh.
Norway. Yeah.
Yes, Norway is very, very. It's pretty exotic, yeah, or I would say very. I think.
Different than US, I think.
I would think maybe the Northwest is very close to that, so probably that way. But I've never been to Northwest so much. Probably in the if you go a little further in the northern part of Canada, it's like that. But yeah, it is pretty impressive. Like I always felt that I couldn't appreciate nature so much when I was growing up because everyone used to say, "Oh, this is great," and I felt, "Oh, I don't see much." But in Norway, I did feel that it was very striking, strikingly pristine. I think very calm and so maybe it is like Himalayas. Yeah, so there are lots of mountains and lots of water.
Fjords, they call it.
Fjords, exactly. What do you know?
Because I like exploring those things. I want to
Okay.
go to Europe. Yes, I can travel the whole Europe.
Or Europe.
Yeah.
You have done it or
I
you
want
want to?
I have a fascination for travel.
Yeah. Fjords are very, very impressive. Yeah. So I did travel Norway good bit actually, but it was mostly friends initiated, but I got to travel. So it was really good. I think the word is probably like tranquil, like you can really feel the calmness, peace. So I kind of like it.
I think life is also slow in Norway than US.
Carbondale is slow enough, I would say. Yeah, I think I like Carbondale. I would compare it with that. And Carbondale is slightly better in this. So Norway, what happens is that the city is designed for a downtown. So everyone comes to downtown and life is in a small region. Like that's how I think in India also it is like that. So you have a small town where around that everything, all the busyness is around that. But Carbondale is nice in the sense it is spread out and it's very peaceful. If you go a little bit outside the city, it's very pleasant and very, again, peaceful kind of. So in that sense, most of the European cities, there's a lot of activity in the town and you have to live around it because you don't have a vehicle there. And transportation is good, but still you live around it. So even though there is a lot of peace, you don't get to explore it unless you're settled. But it is, yeah, at least Norway was very
How many years you stayed in?
I visited every summer there almost for 7 years or something. Right? So
Every summer?
since 2013, I think I stayed there for 6 months continuously once. And since then I've been visiting every summer until the pandemic. So we had some grant there and there was a collaboration, strong collaboration. Hello, Ken.
Hello.
Yes, how are you? You feeling better?
I'm sorry.
Are you
Yeah, I'm feeling a little better. I'm feeling a little better, but I'm not like I'm not really like not feeling super good, you know.
Okay.
Yeah.
I think whatever we are going to do today is going to be very similar to what you have already seen in classical mechanics. So look up your notes there. It's going to be pretty much the repetition. So if you feel you want to remotely attend, that's remotely in the sense you don't want to pay too much attention, might be okay. So yeah, relax.
Okay. Thank you.
If you're paying attention, then let me know if I'm not remembering to move the board. That might be the only catch. So just to complete that point, I mean, since I have been to Norway, I have always wanted to be in Himalaya. I always thought that Himalayas must be the version of that. So I have a desire to do this.
Yeah, I think
They are larger. Height of the Himalayas are larger than the Himalayas in Norway.
Of course, the mountains, and yeah, of course, yeah. The only difference could be the water plus. Like there are fjords, as you're saying, so there is deep water and mountains together. So that's a little, but I'm sure mountains and the glaciers have its own way of presenting.
you were tried climbing.
No, never. I'm close to the mountain. Like Himalaya.
So
I've
you
seen
live in a
from far.
valley?
I have seen from the far. Yeah, my place is like Himalaya are too far from my place. Or I didn't went too close, but I can see from far distance.
I have a question.
Yeah.
If I had subliminal and supraluminal speed, is it going to cross the speed of light? Supposed to cross the speed of light?
Subliminal and superliminal. One is subliminal.
1/2 and 3/2.
I'll try this. Right, I don't know. 1/2 and
3/2.
so this is the way you do it, right? So one is this. So you will start from here and do that, right? And 1/2 and
3/2.
So let's say here. So that's here. And these 2 points wherever they intersect, right? So apparently here, it's superluminal apparently. It's very non-trivial. It is not intuitive, right? Why would that happen?
Yeah. I had every other velocity, none of them crossed the speed of light. But this one crossed. I was confused. You supposed to go like this one.
Yeah, I think you're correct. Yeah. That's why I don't have an intuition for it, but if not for this diagram, the intuition is even worse. Right? This diagram little bit gives you the mathematics of the equations, but yeah, I don't have too much intuition on that.
1/2 and 3/2.
Yeah. I mean, C considered as one, so subliminal is lot in C, superluminal is
Correct.
in C.
So I think you might be right in the saying that it's a theorem that whenever one is on this side and one is on the other side, it will always be on the outside. So subliminal and superluminal probably is always superluminal. I think right. So this you can take this wherever you want. Right. So for example, even if I were to place this here, it will always cut it in that sense. So I don't think you can have a 2 points on the circle here like this, where it will cut inside. It will always cut outside. Probably usually it will prove. But the another piece was if there are two superluminal plus superluminal, that was subliminal.
Yeah.
Why I don't know.
In this question, we need to write answer in terms of numerical data, or we can express.
Numerical is if you want, and in general is better. Like I expect the answer to be general. Like for example, what is subliminal, superluminal? It should be superluminal. So that's a more general statement than if you take a value 1 by 2 and 3 by 2. But you can test it. That's good enough.
Basically doing the same thing.
Correct.
From that figure, we can guess either it is less than speed of light or.
That should be okay. Yeah, I think my motivation there was to just make you explore various things. That's all. And just to, I always like this piece. Otherwise, if you work with equations, it's okay. But this gives you a more powerful way of looking at it. And also because this has been done by a professor in the math department, so it's kind of neat that we have someone local and it is his creation. Like it's not that he's using someone else's result. He was playing around with it. He just discovered this. It's kind of neat, very neat actually.
Yeah, it's fun working. Also, it's quite easy.
Exactly.
Paper, to be honest, how it derived it, I didn't understand that well.
Yeah.
But I mean, understanding what he is trying the theorem is not that tough.
Exactly. That's good.
I have another question.
Yeah.
On the what is the relationship between the boost and the rotation?
Boost plus rotation always gives you a, what was it? Boost and rotation.
How this connects, I mean.
Oh, how do you connect? I think I typically give the following example. So the question I think Ken is that what's the connection between boost and rotation? So let's consider the following. This is considered as a paradox, but it's not really. So let's say there is a window, right? So this is a train, and it has a small window or a door or something like that, right? So it has a length L. So in a static frame, it has a length L. Let's say this is moving with velocity v. So that's a v1. And now you say that there is a brick which is exactly of the same length. Okay. And you say that this is moving in this direction, throwing the brick that direction. Now you argue that, oh, in this frame, right? If I'm in this frame, this is moving with velocity v1, correct? So if this is the one that is moving, it's going to contract. Like the brick will contract and it will go through the window or door, right? Because this is contracted. But now you argue that, oh, that's not the correct way. In the reference frame of the brick, this is the one that is moving. So this will contract, right? So this will not be able to. So it seems like physics or what happens depends on whose reference frame you're in, which is not okay, right? Always it should be the same thing. Like whether it goes through or not, that should be independent of which frame you choose. So that's a paradox. But then the point is that, oh, that's not correct. Analysis is not correct because this is a velocity, that's v2. So this is not normal boost. This is a boost in x direction and this is a boost in the y direction. And these are two boosts. And now what happens is that when two boosts do not work like the normal boosts, they don't add up. Instead, this is a boost plus a rotation. So this brick will actually rotate when it is going through. So in either of the frame, it actually goes through. It will actually rotate and then, yes, it expands, but then it rotates and then it penetrates through. So it can be shown that it is the same. And how you show that is that, so boost, which is n, right? N comma rotations is what? N comma rotations is a boost itself, right? N1 N1, N2 is a rotation. So 2 boosts is a rotation, 2 rotations is a rotation, and boost plus rotation is a boost, I think. Boost plus a rotation. Boost. I don't know. I don't remember. Check. Okay. I think it's there in most of the textbooks. Yeah. How do we make this a quiz? What is it there in the homework? Did I ask you guys to get that?
The second one.
This one I did, right? So that is to show this. N1, N2 is R. But look up what is a commutational relation between boost and rotations. Either it's a boost or a rotation. I'm trying to do that. If there is an analogy there in the physical sense, I can see there might be. Yeah, I don't. Yeah, my guess is it's a boost, but I'm not sure. Okay. Yeah, and it might be a boost. Yeah, it's a boost, not in, yeah, this is epsilon ijk. So this is I, and that's j. So this is epsilon ijk and k, I think. So a boost in the x direction and a rotation in the j direction probably is a boost in the third direction. But check on this. Like I've done this in quantum mechanics, yeah, but I'm not getting a good interpretation to tell you. Rotation and rotation is clear, right? What is rotation?
J1, J2.
Yes, exactly. So this will be again epsilon ijk or k. There are some factors I. Rotations, you can think of it like this, which is probably clear. If you have this paper, now I'm going to rotate. So you remember we started from here, right? So first let's say this is x, that's your x, that's your y, and z is coming out of both. So first let's rotate about x and then about y. So rotate about x by 90 degrees, let's say. So let me rotate in that direction. So that's 90 degrees. And then about y, 90 degrees. Again, let's do like this. Now remember this position, it is facing down. So the page is facing down. So now let me start again. First do the y rotation and then do the x rotation. And now it's not the same, right? So that's the idea of these two rotations not communicating. Yeah, so let's leave this as a quiz. Simple quiz. I posted a homework of 5. Most of the homework 5 will be covered in the class, at least a good bit will be covered in the class. And the problem 2 will be you will have to work on your own. But again, it is relatively simple. It's like the problem that you were discussing about graphically doing it. It's mostly graphical. You don't have to really analytical. First part is relatively long analytical, but mostly we'll cover that in the class. So that's all. And there is a midterm. So this is the first Tuesday after the spring break. And 2 weeks from then, we have the midterm. Okay, so we talked about Lorentz transformation. So this is broadly, you can call it relativistic kinematics. So the idea is this is relativistic like remember what we do in Newtonian physics. First thing we do is define time. Like if you broadly think of it, you define time, right? Then you define position, like let's say x. That's position time, and position is a function of time in a sense, right? How does the position change with time? Then you define velocity. Then you define velocity, which is basically derivative x with respect to time. So these two are, I shouldn't say we define it actually. This is pretty much, we say there is time, which is the only thing we require is that it should be monotonic. It shouldn't go back and forth. It should keep increasing, but we don't really define it. We just have an intuition for time. Same thing with position. It's a function of time, but otherwise it's not really defined. From this point on, we define v is dx by dt. Right? That's well defined. And acceleration is derivative of velocity with respect to time, very well defined. So these two are well-defined quantities. From that point on, again, what is mass? We don't know. Like we don't really strongly define a mass. Like we say that something that has occupied space. It's again an intuition. We don't strongly define it. So it's not clear what mass is. Again, what is force? We don't know. Right? We don't really define the force. Right? We say that something that pushes something, effort that you put into that, that's the idea of a force. But then comes the connection between these three. That's Newton's law. Right? We say that mass times acceleration is equal to the sum of forces. F1 plus F2 plus so on. So that's a well-defined quantity. So this plus this, and the remarkable thing is that starting from Newton's law, we can actually predict so many things. Almost many things that we see around can be explained using this. All the planets' motion can be predicted to significant, to the third significant digit. You can actually predict those things. So it has been extremely successful theory in that sense. Somewhere, so this was given all in probably 60s, when Newton was about less than 25-year old, I guess. So probably 1665 or so. Right? That's what 1660s. Right? 1665 or so he gave all this, and again it is extremely successful. It can explain things to third or fourth significant digit. Then came Einstein in 1905, and he gave the principle of relativity, and he said that it's not Galilean relativity that is true. So all these equations are, there is a Galilean relativity that's I should say the same time there is Galilean relativity. Right? So the principle of relativity based on this is x prime or z prime or x prime z prime. Let's see. Doesn't matter. Yep. So z prime is equal to z minus pt, and t prime is equal to t. Right? That's Galilean relativity. The basic idea here is that if two people are moving with respect to each other, whatever I see will be the like if you change v to minus v, you get it. Mostly you get that. Or there is a it should be, or physics should be independent of who is observing. That's a more strong statement than saying that if one is going in that direction and the other is going in that direction, you get things by replacing v with minus v. Einstein in 1905 realized that this is no more the case. Yes, Krishna.
You read the original paper of Einstein. His original paper.
Yes, in a sense. I haven't followed it thoroughly. But yes, I have looked into it and it's pretty, and problem is that it's not completely, there are translations of that. That's a good part these days. So the translations of that. Yes, I have looked into it, but I wouldn't say that I studied it from there. So I've looked into it. It's useful because not to understand the physics part of it. The challenge usually is that, like this is a discussion I have with UREC, like the faculty who did that rotational, the circle and that one. So the question that you can ask is in 1880. So first of all, Maxwell did the whole thing in 1865. He gave the Maxwell's equations in 1865. By 1881, Thomson suggested that electrons are moving and there is an electric field with it, so you can associate a mass with it. So you can associate an inertia for the electron. And since then, everyone has been associating most of the physics that they were understanding with the ether. So the idea was that there is something special because they were all biased with sound. Right? Sound has a medium, and that medium is special. If the medium moves, source moves, everything moves. So everyone was wanting to say that we are in a vacuum, and that is still, like, as far as you're in that medium, it is all static, and we are all seeing things relative to that, which is against this relativity. Like, relativity doesn't say that. So it was against relativity, but they were trying to interpret those things. Lorentz, for example, this is called Lorentz transformation. He had this in 1893. He derived everything, but he could not, he was not ready to give up this. He was interpreting the whole ether. They were giving structure to the ether, the electron model, everything. Poincare had the velocity addition formula in about 1903. He almost was ready to give up this, or ready to give up the physics of the ether and come back to that, but he was not strong enough. And then Einstein came in 1905 and did this. So usually the argument is, for example, UREC would make the case that Lorentz transformation existed already, Poincare existed already, so why give the credit to Einstein? Right? He did not do anything new. Like everything he did was already there. But I argue that no, the central piece, that the central theme in which you do it, that the ether is completely rejected, was a big leap. Even though every equation that he wrote down, you can relate it to something or the other in the past. I would argue that no, that jump was extremely significant to you. That's it. I see the argument on both sides, and it's not an argument really, it's just a curiosity as to how did this whole history come up. That is so often it is hard to see what goes on in someone's head, right? Like papers, of course, you can read as you asked, but how did people think along this line? So there is an interesting story. I think I will encourage you guys to look up. If you, like, Einstein was given a Nobel Prize in 22 or something, and then usually the Nobel Prize, you have to go and give a Nobel lecture, right? And based on after that, there is a ceremony and all that. But it's an interesting point to note that he had a appointment with Japan, or he was supposed to give a talk in Japan during that time. So he did not cancel that. So he canceled his Nobel lecture and instead went to Japan. And that lecture he gave, it is an informal lecture. He just talks about, it's a discussion between him and some faculty in the university, Kyoto University, I think. And they just talk to each other about how did you discover relativity. And the people who took notes, that were detailed notes, and then they publish that paper. That's sort of a measure of a very colloquial, in colloquial language, you see what he was talking about. And he mentions these things that, yeah, Lawrence was there, pointed out that all these equations existed before, and how he was discussing with his friend and how he came across. So it's useful to think about those things, but yeah, and he has a book also on this, like Einstein has given lecture notes. I think he gave lectures in Princeton after relativity. So yeah, it's good to read those things, but often slightly tricky to. He surely understood all the electrodynamics, because that's what was the basis of it. Does that help?
Yeah,
Answer? Yeah.
this is the, I mean, this is a theory or concept in physics. I feel like everyone can access it. I mean, it's normal algebra in a sense. I mean,
Yes, now, yeah, this is one of those theories where the mathematics is simple, but the
intuition is good.
yeah, intuition is extremely non-trivial or counterintuitive, kind of. It's not daily life. So once you, that's where the geometry helps, right? I mean, once you have the circles and all that stuff, helps to. It's almost like saying, how do you see the fourth dimension? It's hard to visualize it, but then you build ways to have an intuition. So yeah, once you play around with it enough, you get some intuition. But surely not like three-dimensional. Yeah, that's true. Yeah. So so what we want to do is, so of course, this was the physics that existed before, and the only change now is that you say that, okay, this is now changed to z prime is equal to gamma times z times vt. It's good to write this as v over c. It's vt, which is good to write this as gamma times z minus beta times ct. So beta is v over c, and multiply and divide that. And d prime, this is a revolutionary thing, that this is no more absolute time. Instead, it is gamma times beta z minus y minus minus beta z actually, plus gamma is already there, so c times t, and this is c times t prime. So that's your time. Like that's the Lorentz transformation. I mean, we have been writing this as a matrix. That's good enough, right? But now the point is, if you change this, everything changes right from the first step, right? Everything changes. So we have to now do the whole of Newtonian physics again. We have to reach here. If you want to solve problems, we have to reach this stage. And the simplest problem we will solve is if you drop a mass in a uniform gravity, then it accelerates, right? You start from zero velocity, uniform potential, it will keep increasing its velocity. That's not allowed in relativity. You cannot go beyond c, right? So something has to stop that. So, and this motion is described by a parabola, right? X versus t in a uniform gravity is parabolic, correct? We will see that the same motion, if you put a uniform acceleration in relativity, it will be hyperbolic. So it won't cross the speed of light, but we want to derive that. So that's our goal. So we'll go back, trace back our steps and get Newton's law in relativity. That's our goal. Okay. So we start with the first step. What is before velocity, we have to do position, right? Position, and we have to at least connect the position and time. So that's our first step. So the first step is go back to this, and we will, or let's have some notation, right? So let's have position and time, right? So this is position and time. Oops, position and time. And we will define this as x mu. So x alpha. So that's x with a superscript alpha. And it's going to be, it's a vector kind of thing. So this is c times t and 3 dimensions x. Okay. This is a superscript. We are going to differentiate superscript and subscript. We will say x subscript alpha. The procedure is going to be change the sign of the time component. So this is time position, right? 0, 1, 2, 3, 4. Usually we will say alpha goes from 0, 1, 2, 3. When alpha is equal to 0, it is CT. So this means that x0 is equal to CT and xi is equal to vector x, right? So that's 1, 2, 3. Is that clear? So this vector has 4 pieces. That's a 0th component, and these are 1, 2, 3. Clear? Question?
When alpha is 1, why is CT 0?
When alpha is 1, tell that again.
When alpha is 1, you written it like xi equal to x vector.
Uh-huh.
So why there is no CT component when alpha is 1?
Because when, or let's say, maybe what I mean is x alpha is this x, y, and z. Okay, correct? So this is going to be x0. This is going to be x1.
Yeah.
That's going to be x2, and that's going to be x3. Okay. So, and sometimes I will also write this as CT times vector x, right? Because this is the usual position that we talk about. And now we are saying time is the 4th component of position. Like if you think of a vector in 4 dimensions, 3 is space and the 4th dimension is time. Okay, so that's a 4th dimension. We will call it the 0th dimension. Right? Either way, it's okay. Right? So alpha goes from 0, 1, 2, 3. A general notation will be that Greek letters like alpha, beta, mu, nu, and all, they will always go from 0, 1, 2, 3, 4. And Latin letters like I, J, K will go from 1, 2, 3. So whenever you want to talk about space components alone, you will use I, J, K, L, M. Whenever you want to do space-time, then you will do Greek letters, alpha, beta, and so on. Is that clear, Pillan? So that's, I'm building the notation. If you, and position, it's important that it's always upstairs. Okay. If it is not upstairs, that means it's not in the superscript. If it is in the subscript, then how do you go from superscript to subscript? Keep all the space components the same. For the time component, you switch the sign. Okay, so this is going to be minus CT times x. So clear? So that means to say that x0 is equal to CT, but x subscript 0 is minus CT. Okay, that's just a notation. And this is true for any vector. So this is often called contravariant vector. Often called a contravariant 4 vector. It's the 4 vectors, and this is a covariant 4 vector. Okay, good. Let's take the dot product of these two. X alpha times x alpha. And whenever I write this 2 times, the understanding is that there is a sum. Right? So this means that this is a sum over alpha going from 0 to 3 x alpha. That's the same as x0 plus x1 plus x2 plus x3. But now let me use this notation. Subscript can go to superscript if I change the sign. So let me do that. So that's the same as minus x0 plus x1 plus x2 plus x3. This is the usual space piece. That's a dot product of 2 x's. Right? So this is the same as minus like x0 is ct, right? Ct squared plus x dotted with x. The usual dot product in space. Clear?
The second line minus, how you put that minus?
I moved the x subscript to x superscript, right? X subscript is minus ct, x superscript is ct. So the connection between the two is minus, right? Because ct is x0, so x subscript is minus of the x superscript. So I use that to change that. Clear?
It's related to like group or something we did last semester.
Oh, that's exactly this. Okay, that was taught so that you find this convenient. Is that clear? That's exactly the same thing. Very good. Yeah, that's exactly the same thing. But here, now we are really at the user level. I won't go into too much into details of that. Here we'll start using it. And there we did a lot more in detail in the sense I did not assume that this is the only transformation. There it was much more general. Here we use only small piece out of it. So this is special relativity. There we were building general. So those techniques are much more powerful, or those techniques are necessary to work with general relativity. Here we are doing special relativity. Like special relativity deals with when we have 2 frames going with 2 velocities, then we say that the physics has to be the same. If you are moving with 3 meters per second, I'm moving with 4 meters per second, both of us see Johnny there sitting, you will see the same thing, I will see the same thing. We cannot conclude different things. We might interpret things differently, but if he writes something and then stands up, I will also say that he wrote something and stood up. The sequence of events will be the same. Is that clear? But the note is velocity, right? Special relativity deals with only velocity. Like the 2 frames has to be moving with uniform velocity. Einstein afterwards said that this cannot be so special, right? This is very special, right? Constant velocity. He said that this should be true anything. Any 2 observers seeing the world should see the same thing, irrespective of whether it's velocity, acceleration, anything, any kind of transformation. And that's general relativity. So he took it to the next. So here we are doing special relativity. So things are very simple in the sense, if you want to go from here to there, it's just a minus. But it's exactly the same idea, same. The formalism we developed there is going to be applied. Okay, so that's your 4. This will be called invariant quantity, right? So notice that this quantity does not change from one frame to the other, right? If you go to x prime, so let's say x bar alpha, right? And x bar alpha. So this is another frame. If you go to another frame, x goes to x bar, and this will be equal to x alpha. So that's the idea of Lorentz. Lorentz transformation, or that's a basic idea we saw, that the way we wrote it is that x prime dotted with x prime minus ct prime square is the same as x dotted with x minus ct square. We showed that in the earlier class. Remember that? Right. So this structure remains the same. So the basic idea is that whenever you have a 4 vector, you can construct this covariant and contravariant vector in such a way that this quantity will remain invariant between 2 frames, which is good. That's what we would like to match. Don't match the distance, don't watch the time. This combination will always remain the same. Okay. So we still, with position and time, we are at this stage now, right? We have to go a lot there for the Newton's law. Okay. So let's do this a little bit more. So we are usually interested in, when we are doing Newtonian physics, in the change in position. It's not the position itself that is important. The change in position in change in time, like displacement in a certain time. That's what is more important. So we will define the idea that delta x alpha is equal to same idea there. So it is delta ct, so delta t times c, and delta x. So change in time, change in position, delta x alpha. And same idea if you say delta x alpha downstairs or covariant, then it is delta x. And delta x alpha is equal to minus c square delta t square plus. So you get the point, right? Once we have a vector, contravariant vector, covariant vector, dot product, and this will remain the same in every frame. This is a finite change in position. We can make it infinitesimal change in position, and that we will call the S alpha, or dx alpha, sorry. Instead of delta, then it is infinitely tiny. X, dx alpha is c dt, and dx. Same idea, but it's now tiny, like infinitely tiny displacement and time. And now you have dx alpha times dx alpha is equal to c square dt square minus plus dx dotted with dx. Remember, velocity is defined in terms of infinitesimal quantities, right? Dx by dt. This is an infinitesimal displacement here. We will call this minus ds squared. It's a minus, so that means we are kind of thinking in terms of time, right? So S will be interpreted as a proper time. Since this is an invariant quantity, so we can say that this is minus ds square is going to be the same in every frame. So this is true, dx, and this is also true in another frame. So it is minus c squared dt prime square plus dx prime dotted with dx prime. Is that clear? Because it's invariant, it's the same, right? As of now, very fine. If it's the same, so let me pull this out. Now notice, so this is equal to, let me do the following. Et squared. So if you think, oh, this is infinitesimal quantity, so you can make it finite and then take the limit, right? That's so it's the idea of derivative is being used here. So this is equal to 1 minus dx by dt squared. And probably something is missing. C, right? 1 over c squared. And it's the same thing in the other frame also. So it's minus c squared dt prime squared 1 minus 1 over c squared dx prime over dt prime squared. This is the velocity in the first frame. This is the velocity in the second frame. So what we have is, so I'll stop writing the second frame now onwards. Right? It's understood that anytime I can go into the other frame as far as I'm working with invariant quantities, right? So I can write this as take square root of this quantity. So this is ds minus gone, right? So ds is equal to c dt times square root of 1 minus v square over c square. All clear? That, remember, is gamma, right? So gamma was, so beta was v over c, and gamma was 1 over 1 minus beta squared, the square root of that. So this is 1 over gamma. So we have a connection here. So ds, how do you say this? Or c dt over, so c dt over ds is equal to gamma. Right. Or better think of it as ds itself. The ds is equal to c dt over gamma. Notice this is going to be the ds is an invariant quantity, right? In any frame, ds is going to be the same, but dt is going to be different in different frames. So this is the idea of time dilation. dt is equal to, so whenever you say dt is equal to c, dt is gamma ds over c, right? So ds is invariant, so that means even in the rest frame it will be the same. Gamma is always greater than 1. So this is the idea of time dilation. But we are not interested in that. That's an interesting concept, very intuitive, very useful. But our main goal is that instead of time, whenever we are doing kinematics, we have to take derivative with time. right? That's the idea of velocity, acceleration. You have to take derivative of time. But I don't want to do that because we want something that is Lorentz invariant. So we are interested in everything remains the same, it is time, but we want to see the connection with something invariant. So wherever there is a time, we will try to do ds. That's what is going to happen. Again, velocity will be velocity. It's not, we are not going to change the definition of velocity. Velocity will remain velocity, but we are interested in invariant quantities. What remains invariant between two frames? So this connection is going to play an important role. So whenever you see time, it is good to replace it with ds, and we'll see how it works. Okay, with this information, and that is all based on just a definition here, or it's not really a definition, it's a combination. Position and time is being put at the same footing. Right? It has very, there is a similarity between position and time, and they transform with respect to each other in Lorentz transformation. Okay, so with that, now let's define four velocity. This is not velocity, this is forward. I would like to insist that velocity will be the same old velocity. In relativity, the idea of velocity does not change. Right? Velocity remains. So velocity is equal to dx by dt. That doesn't change. Okay? This is for velocity. It is like position and time work together. What is the fourth component of velocity? The fourth component of position is time. This is a vector, 3 vector. We are interested in asking what is the fourth component of velocity, because that's important, because that combination is going to stay the same. Right? This combination stayed the same. If this combination stayed the same in different frame, if we can search for a fourth velocity, then the combination will remain the same, and that will be the idea. So let's define four velocities. So this is a definition. So u alpha will be defined as dx alpha. This is a change in 4 position. If I were to divide it by the normal time, then it won't be invariant. So I divide it by ds. Okay. Because ds is an invariant quantity. Now, I would like this to have the dimension of velocity. This is length. ds is also length, right? ds is also length because it's like dx. So I need the dimension of velocity, and that's why I put a c. It's just a definition, so I can do whatever I want. But we will see that this has the product of these two will remain the same. So what is this equal to? What that means is that, so let's see what this means. So this means derivative with respect to proper time of x alpha was ct, and this was x, right? That's what this means. Right? Take the derivative in. This means c square dt over ds, like change in time with respect to the invariant time. And this is c times dx by ds. Agree? But we are interested, or we said this is velocity. This is with respect to s. This is not velocity yet. So use a chain rule. Right? So let's use a chain rule. So instead of going this way, we again come down here. This is the same as dx by ds will be dt by ds times dx alpha over dt. So the idea is whenever I want to get the derivative with respect to the invariant time, I'll use the chain rule. and do it with respect to the normal time. And then what is c dt by ds? That we did already, right? C dt by ds is nothing but gamma. So this is nothing but gamma, c times gamma times yeah, I think so. C dt by ds, yeah. So c times c dt by ds is just gamma, right? Sorry, yeah. Just gamma times d by dt. So this is d by c dt by dt, and then this is, let's do this one. So this is the same as gamma times dx alpha over dt. I'm just replacing that. And d by dt, so this is the same as gamma d by dt of c t comma x. Derivative of time with respect to time is 1, and derivative of x with respect to time is velocity. Right? So I get my fourth position to be gamma times c, and that's velocity, the usual velocity, that the Newtonian velocity. We will often write this as u alpha is equal to c times gamma, velocity v times gamma. So again we ask, what is the fourth component of velocity? It is c times gamma actually. Right? It is, remember, what is the fourth component of time? It is not really time, there is a gamma sitting there, right? ds has gamma in it. Like this, there is this gamma sitting in front, right? So that's the same feature we're seeing, gamma. If this is the case, what is the invariant? That there is an invariant length, right? ds square remains the same. There must be something invariant there. So let's see what is u alpha then. U subscript alpha, or the covariant alpha. So that's the same as minus c gamma times b gamma. That's what it is, and which means that I can combine these two, and this should be invariant. This should be independent of which frame I measure. That's interesting because that's a new quantity we are going to derive, right? Whatever this is going to be independent of which frame you measure. So that's interesting. So let's see what this is. So this times this, right? So our idea was just this times this and this times this. So it is minus c square gamma square. And this dotted, right? So this is plus v dotted with v. So that is v dotted with v times gamma square. Okay. Get the minus c square out. Get the minus c square out. And gamma square also can come out. And I have 1 minus v dotted by c dotted with v dotted by c. That's for nothing but beta square. That's minus c square gamma square 1 minus beta square. Agreed? What is gamma square multiplied by 1 minus beta square? 1, right? Because gamma square is 1 over 1 minus beta square. That's exactly 1. So this is minus c square. which is great because we said this has to be invariant in any frame. Of course, speed of light does not depend on the frame, so it is minus c square. What does that mean? Remember, we had time-like quantities. So if you had a frame and this was CT and this was X, let's say, right? And so we have this 4 regions. In this region, CT is greater than X, correct? Like a magnitude of CT is greater than magnitude of X. In this region, CT is less than X. So if you were to say this ds square here, so ds minus the ds square is c dt square minus dx square, right? In this case, this is c dt is greater, so as df square as possible, right? Huh? No, but here it is. So this is here ds square is less than 0. Right? Is that correct? Did I do this right? I think so. So what am I saying? Yeah, so actually, yeah. This is ds square, right? Or yeah, I mean, this should be compared with minus ds square because this is minus ds square, right? So the square, this times this is a negative quantity, right? So the way to see this is that this is minus ds square. Yeah, minus ds square. But this is a minus and a plus. Minus ds square is greater than 0, then it is actually, which means that ds square is less than 0. Right? And that means that this is called time lag. So this region is called time lag. Anything that is in these 2 cones is called time lag, and these 2 cones is called space lag. So the basic idea here is that the 4 velocity that we constructed is a time-like quantity. Right? So this implies that this is time-like. So this means that U alpha is time-like. So the basic idea is that time is stronger, right? This is a construction we are building using time, a time component and a space component, and this is larger. That's why it is negative. This is larger means the time is larger. So here, I think when I substituted a minus sign, I should have switched the sign. That was the idea, right? So that was a mistake. Clear? So this is a time-like quantity. So what we have shown is that velocity, we have constructed something concerning velocity which remains the same in every frame, which is turns out to be obvious that, oh, it is the speed of light. Okay. But that's not very far, because now you are here, right? Suppose you go from here, you can now, before you go to acceleration, right here, you would say position, time, velocity, and the next step is immediately acceleration. And then you do various things, right? I mean, this is of course Newton's law, but then you do momentum, and then you define energy. Right? There's a lot of concepts you derive, right? We can immediately address momentum here, because momentum is just mass times velocity, right? So here, let's talk about in the last 2 minutes. Let's talk about 4 momentum. For momentum is going to be P alpha is just simply going to be m times u alpha. This now becomes, we know what is mu alpha, so that's m times c times gamma, and this is velocity times gamma. Oh, I should emphasize that m here is a constant. Often you will see, especially in undergraduate textbooks, this, or not even undergraduate textbooks, not in physics undergraduate, at a very popular level, it is convenient, or actually not only popular level, even Einstein used Einstein's paper. In Einstein's paper, it is m changes with velocity. It was convenient for him to define m changing with velocity. There's nothing wrong if you play it with it correctly, but what we are going to hear is m is fixed, m is constant. So m is a rest mass. That's what he will say. It doesn't change. It is not velocity dependent. It is not velocity dependent. It's not frame dependent. M is m. That's it. M is a constant. That's what we want. So in this sense, so this is m c gamma, and this is m b gamma. Now this is all fine. When you think of 4 momentum, your hope is that you would see the normal momentum here. You do see the normal momentum here, but with a gamma, right? And this is where the physics changes. Until here, I have just constructed things. But this is where Einstein connects it with physics. So this is where the physics comes in. This is the contribution, or this takes some effort, I think, from connecting with physics, and that is that you say mc gamma is energy, and this is momentum, not the. So this is, so what we have done is P relativistic, right? Relativistic is going to be m v gamma. P Newtonian is just mv. So I want to emphasize that these are different. From this point on, we'll stop writing relativistic. T always means mv gamma. This is gone. This is Newton's physics. This is a change. Velocities remain the same, but momentum is not. This is not dimensionally correct. To fix that, you said LC. So that's your new physics. So this is your P alpha. So earlier we have what's the 4th component of velocity. That came out to be not very interesting, but what's the 4th component of momentum? That's energy. And that's significant. And now you can say, oh, what is P alpha? Because that's going to remain the same, right? And that's nothing but minus E squared over c square and plus p dotted with p. That remains the same in every frame. So that's interesting. One would ask, what is that equal to? You can go back here. That's the same as m square u alpha, right? Because that's the first line. What is u alpha minus c square, right? Right. So this is minus m square c square. Rewrite this, and you learn v square is equal to p square c square plus m square c raised to 4. Right? That's a famous Einstein's relation. Often that's what I said in popular physics. You define your momentum so that define your mass so that your p is there in it. Right? So you often write this as E is equal to mc squared. But that's true only in our way of doing. This is for p equal to 0 or v equal to rest mass. Right? The energy, even when you are, so this is if you want kinetic energy, even when you're in a rest frame, there is a mass, so there's an energy associated with mass, right? And that's the idea of an atomic bomb. Immediately it was realized that to convert mass, if you make the mass disappear, then you will generate energy. And that was the idea of atomic bomb. Horrific, but a very deep concept, very nice concept. But it was been used in a horrific way, if you want, but a beautiful concept. We'll come back and start from here. So we have now velocity, we have momentum, we'll define acceleration, we'll define force, but the idea is going to be the same. Wherever there is a time derivative, we'll make a proper time derivative and get the Newton's law in this case and do some problems. Okay. That's all. Thanks.
I have a question.
Oh yeah, you have questions. Yeah, I was thinking you will be not relaxed. Yeah, go ahead, Ken.
Yeah. So has anyone ever done this with like the quantum mechanics definition of P?
Yes. This was done by Dirac.
Okay.
So Dirac did the right after quantum mechanics came in 1926, like Schrodinger and Heisenberg wrote down the non-relativistic physics in quantum mechanics. Dirac, within 2 years, I think 1928, he wrote the relativistic version for it. And the interesting part is that spin becomes spin, the property we associate with particles, that becomes intrinsic in the equation itself. Dirac equation has that at the intrinsic level. So very beautiful, actually. Yeah. So Dirac is the one who extended it to relativistic quantum mechanics.
Okay. Yeah. Thank you.
And then the challenge comes, what about electrodynamics, how it works? That was the hard part. So the quantum electrodynamics becomes very, it has a lot of new techniques you have to develop. That's quantum field theory, where you do quantum mechanics in the relativistic quantum mechanics and electrodynamics together is quantum electrodynamics. That's the idea of quantum field theory. Okay. Yeah, good.
And I actually have another question in regards to the homework.
Yes.
It's just a clarification. So for number 2, you talk about is the addition of velocities commutative. Are you referring to like relativistic velocities, or just just normal kinematic velocities?
Normal kinematic velocities, but it is relativist in the relativistic context, but the normal velocity, the 3 velocity, if that makes sense.
Okay.
Usually we always say 3 velocity. It is good to see that there is a 4 velocity, but physics is usually done with normal. Measurements are made for velocity, normal velocity. Momentum changes its definition. That's the basic thing. And energy changes its definition. But at the velocity level, things remain the same. Does that help?
Okay. Yeah, I think so. Thank you.
Okay, good. Take care. Yeah, hopefully you get some time to rest in spring break, but there's a few more days for that, right? Yeah, hopefully you'll get well before. Yeah. Okay.
I have one.
Yes.
So let's say the equation E equal to mc square.
Yes.
You're explaining it to someone who knows nothing about physics. So how you will explain? How bomb will how this equation actually transform into a bomb?
Earlier, before this came, before this equation came, the idea was that energy is associated with motion.
Yeah, that's it.
Right? So if you want to create energy, what you would do is make something go very fast and come and collide, make it stop, right? So when you come and make it stop, then it has to release that energy. And that was the idea of like a rifle, for example. Something going very fast comes and hits you. And that's basically the idea of a bomb in a kinetic
Fusion or fission?
fission. So now what we are saying is that M also has energy associated. Just because you have mass, you have energy associated with it. So to generate energy, what you would do, you have to disappear. That's not easy, right? You cannot disappear. In atomic or at a nuclear level, there are reactions that happen where mass disappears. Like initially there is a mass and then it converts itself into another nucleus and a small amount of mass disappears. Where does it go? It is released as energy. So if you can harness that, if you can control that, then you have a bomb. That's exactly what was done.
So basically, if I can vanish something,
You will have energy. Exactly. So for the best, easiest is an electron, right? This is an electron. Antiparticle of that is a positron, right? So this is E minus, this is E plus. Right? Come together, they will annihilate each other, but they have mass. So that's energy. They have to create energy. So this is shown as an electron comes in, proton comes in, they annihilate, they create photon. That's a photon. Because photon doesn't have mass, right? But it has energy. And that's the reaction you would show. But then the idea is this is only one photon. Momentum also has to be conserved, so there are more things to that. But yes, so if you want to generate energy, just disappear.
this there is other implications too. That means humans or animals, anything that has life and you don't have any life. So according to this theory, you can easily separate.
Careful there, notice when we say no life, the atoms are still there.
Yeah.
Mass doesn't change, right?
Yeah, but still life, it's a metaphysical question.
Yeah. So does the mass change? That's all. Here the only statement is that mass has energy. There it is slightly deeper, right?
Yeah, but I can't just vanish myself. I cannot also vanish.
Correct, exactly. That's why it is harder. Like that's why we don't see it in classical physics. That's why you have to go very fast to do this. Or this is more common when the velocities are in the scale of the mass. Usually this is so large that this doesn't even change anything. Like velocities typically are very small, so you neglect this altogether. So we'll do that. Next time we will come and say that, okay, this is your energy. But I thought in Newtonian physics, energy is equal to P square over 2m. So how do you go from here to there? Right? In some limit, you should get that. Right? So we will talk about that. So when velocity is small, we will actually get that. So it's a good exercise to do. In what limit do you reach that? So that's a non-relativistic limit of this. So it's important. Yeah, we'll talk about that. Okay.
According to the, I mean, Hiroshima and Nagasaki bomb, they use the plane to actually drop the bomb.
Correct.
So in a container, they actually conserve the energy. So when they drop it,
Oh, no. So the idea, it's not that, no, it's energy is not contained in the, no. So there are, so very, like it's a 1 gram of radioactive material. It's just a matter of triggering, right? So for example, what's the reaction you think of? Let's say uranium, right? I'm not sure what's the reaction, but let's say uranium 93 or 92, let's say. How much? Oh, that's an atomic number. I think, yeah, so that's the point. I think, is it 92 or?
Yeah, 92.
And this is 245, is it? Now the point is, this under radioactivity, this remains the same, I guess. One of the neutron becomes, how do you say this? I think this splits into 2, right?
yeah.
So this splits into 2. Let's say there are 2 atoms, okay? So let's say A, 2 times A is broken into 2 atoms. But then there is a neutron that is released. Now, if you measure the mass of this, let's say M initial and then M final, that is less mass on the right hand side. Okay? And that means energy is released. Now, the good part is that, yeah, if you now, okay, so if you, this typically happens at a random level. Okay, so then it's not good. I mean, then you don't have any control on this.
I mean, radioactivity is a random process.
Is a random process, right? But the idea here is that this requires a neutron, right? You need a neutron for this. I think it's neutron plus something. Probably, yeah, there's, yeah, plus, that's it. Let me say 3, I'm not sure, okay? So the point is, you start with a neutron, it hits this, but these 3 neutrons can trigger more neutrons.
It's a
It's a chain, right? So as far as you have uranium, this will keep going. So it's a chain reaction. So if you have 1 gram, which is a lots of uranium atoms, if you can control this, it goes in a cycle. That's why it's a bomb. Right? The moment you trigger it, the whole thing is. But it's only 1 gram or something. So what they did is, in that container, that's a 1 gram of uranium, and then you just trigger it. It's exactly like a firecracker. You burst one, and the whole thing is gone. Right? So once, and that is only controlled by how much of this is there. So, and that's why, and the idea was that for this reaction to happen, it has to be very pure. Like you want this uranium to be very clean, like there should be perfection in it. And that's what the most of the time was spent in making this. I think, what is this called? I don't remember the words for this technology. Yeah, but get the uranium, first of all, that was, and there I think used plutonium, if I'm not. Very close to us, I mean, here, right? Oak Ridge, that was where they used to do this. They basically, what's the word? Making plutonium cleaner and cleaner. That's a understanding of that, but I think there's a word for that. Then basically, and this is neutron, so trigger it. So yeah, in that bomb, there was just 1 gram of uranium.
Yeah, 1 gram of uranium changed the human history.
I agree. And after all that, one realized that, okay, there was so much, okay, we will never touch it, but now today is not a bad, it's a good time to teach this because we are really talking about these things and people are crazy. Yeah. So, yeah, I hope.
Yeah. Thank you, bro.
Yeah. Good questions.